Hey everybody, I'm trying this out again. It's my third test. Hopefully it works this time. This is my first time trying Screencastify, and hopefully it uploads to YouTube. My last few attempts, it didn't work. But anyway, we're starting a new unit, Earth's interior and plate tectonics. And we're first going to learn about Earth's interior. So if you look at the handout or the document that's uploaded for today, these are some images about Earth's interior, different ways we can view the Earth. So this image right here, let me get this thing, in the lower left, that's the Earth with a chunk or slice taken out. So you can see all the different layers from the crust into the core. And that is brought over here. So let's talk about the crust to the core. So the crust is the outer edge of something. So you should be familiar with that term, like pizza crust or the crust of bread. So you should know the crust is the outer layer of a material, not just the Earth. So our crust happens to be extremely thin and fragile. So the crust is the thinnest layer of Earth. It's solid, and there's two types, in the ocean crust and the continental crust. And it's also broken up into pieces that we call plates. To give you an idea of how thin the crust really is, imagine Earth was the size of a basketball. The crust would be the thickness of a sheet of paper around the basketball. So that's how thin and how fragile the crust really is. And unfortunately, we are sometimes reminded about how thin and fragile it is when we have earthquakes and volcanoes. So then we can tell how easily it could get broken. All right. A lot of times people use this term lithosphere as kind of a synonym for crust. They're not exactly the same thing, but for the most part, you could kind of think of them as the same. Lithosphere has the term lithos and sphere. Lithos literally means land, and sphere means region. So this is the land region of Earth. There's also the hydrosphere, that's the water region of Earth, and the atmosphere, which is the gas region of Earth. So the region of Earth that has the land that we could walk on, is called the lithosphere. And really, it's not just the crust, if you look here. It's the crust and mantle, but the uppermost part of the mantle. We call it the rigid mantle. And it's this portion that is actually broken up into these pieces that we call lithospheric or tectonic plates, which we're going to learn about. Okay. Now, as we head on down into the Earth, the next layer we come across is called the asthenosphere. The asthenosphere is nicknamed the plastic mantle. The mantle is the largest or thickest layer of Earth. I always remembered mantle from associating the M for the middle layer or the layer where the magma comes from. So M middle and magma, that's your mantle. But specifically, the mantle comes from this area called the asthenosphere. And this is the part that can actually move. So there's boiling magma under the ground, and this is where it's coming from, the asthenosphere. Sometimes it comes up as the form of a volcano, and sometimes it just moves the plates or the pieces of the crust above it. And that's how we get earthquakes. All right? Beneath the asthenosphere, this diagram's calling it the mesosphere. You're going to study this chart over the next few days called the inferred properties of Earth's interior. You're going to get a chart. I'm going to do another type of video to teach you how to read this chart. And in that chart, instead of calling it the mesosphere, it's called the stiffer mantle. Okay? We really don't know much about it. So I'm not going to test you a lot about that layer. Anything you'll be asked about it, you can get the answer directly off of the chart. So like how hot it is, how deep it is, the pressure, all these answers are, as long as you know how to read the chart, like I said, we're going to have a long lesson on it. It'll probably take 2 days to really get good with it. Those answers can be found directly on that chart. So just to summarize up to this point, we had the crust, which is really part of the lithosphere. And then under that is this boiling magma layer called the asthenosphere. And then this solid part of the mantle, or it's called the stiffer mantle. And then eventually we get to the core. Now there's actually two types of core. There's the outer core and the inner core. And just by looking at this diagram, they tell you why there's two types. One's liquid. See that? Second. Getting new to this thing. See right here? It says liquid. I just crossed it out. Wonderful. And then down here, it's inner core, and it says solid. Okay? So the outer core is liquid, and then the inner core is solid. And this should be my eraser. And hey, learning how to use this. Okay? And the center of Earth is about 6,371 kilometers down. Now, we've never been anywhere near that. We actually have never drilled through the crust. And the crust can go all the way to 100 kilometers, which is about 60 miles. Okay? I'm not exactly sure how far we've dug. You can look that up if you're really curious. This other picture, right here, is actually showing you the interaction between the asthenosphere and then the lithosphere. And it's actually these two layers that we're going to spend the majority of the unit learning about, because it's the interaction between the asthenosphere, which is the boiling magma, and the lithosphere, which has our solid crust, that really causes the earthquakes and volcanoes and the overall understanding of the theory of what we're leading up to called plate tectonics. So we're going to spend a lot of time learning about how the asthenosphere interacts with the lithosphere. And in this picture, they're showing you ocean crust, that it's thin, and continental crust, that it's thick. Okay, so now scrolling down to the next page. And if you were paying attention, I said we've never actually dug down past the crust. So how in the world then do we know what's down there? Like, how can we say the outer core is liquid and the inner core is solid, or made of iron, and one's made of nickel, or that there's a lot of silicon and magnesium down there in the mantle? How do we say all that stuff? Well, we only get one piece of direct evidence of inside the Earth. There's only one thing on Earth's surface that kind of tells us what's beneath the surface. And most of you probably know this answer already. Volcanoes. So you should fill these out as I'm filling these out on the sheet you have on the attachment. You have this attachment as well. You can always pause the video and bring it up. So studying volcanoes. Studying volcanoes tells us a few things. It tells us, for one, obviously that it's hot, right? That's obvious. Inside the Earth. Let me get rid of this thing. Okay. And what else does it let us know? Okay. Sorry about that. Like I said, I'm learning how to use this. It tells us a little bit about the chemistry inside the Earth. You know, like gases and minerals and other elements. Okay, so for example, if we see a volcano erupting, well, we know the volcano came from down below. So if we see certain gases coming out of that volcano, and those gases don't match the gases in our atmosphere, then we know that, hey, things beneath us may not be exactly like things we see either in the rocks we're looking at or in our atmosphere. And also lava, which comes from the magma, eventually turns into rock. So the chemistry of those rocks, which are the minerals in those rocks, tell us a lot about the chemistry that is deep beneath the ground. So studying volcanoes give us a little eye or a little look into the inside of the Earth. The second one, in my opinion, is the most important piece of evidence or information that we can gather to tell us about the Earth. And I always like to use this example. Let's say I broke my arm. Now, obviously, I'm in a lot of pain. But if the bone didn't literally break the skin, how in the world would I know that it's broken? Well, you should all know this. You go and you get an X-ray, which is a picture using waves. And you trust the doctor and you trust the machine that took the picture that, hey, that's a broken bone. And we're at that point with technology that we don't even question it. Well, we kind of do the same thing to find out what's inside Earth. But instead of taking an X-ray image of the Earth, we use another type of waves called seismic waves, which are earthquake waves. So by studying, by studying seismic waves, which are earthquake waves. Okay? So earthquake waves will behave differently when they come across different material. So if there is a big solid ball of iron inside the Earth, don't you think if a wave was to hit that, it will act differently? Just like if an ocean wave was to hit a wall on the beach, it's not going to maybe go through the wall. It's going to bounce off. Well, the same thing is actually true about these waves called seismic waves. These waves will travel through the Earth, and when they come across different things, they're going to behave in a different way. And that allows us to kind of get a picture of what might be down there. All right. We're going to spend a whole couple of days. It's just like a real subunit learning about the different types of seismic waves. So for right now, just know that it helps us know what's inside the Earth. So by studying seismic waves, it gives us clues on what's inside. All right. All right. The third one is Earth's magnetic field. Okay. So Earth has a very strong magnetic field that surrounds us. Okay. So that's strange because there's only 3 elements that are magnetic: iron, nickel, and cobalt. And the problem is we really don't see any of those materials or elements on Earth's surface. What I mean is, if we went under the assumption that all of Earth's crust was the same thing through and through, so if the rocks we see on Earth were the exact same thing in the core, we would not have a magnetic field because we just don't have enough magnetic elements. But we actually have a very strong magnetic field. So that tells us there has to be something magnetic inside the Earth. And we believe it's caused by an iron and nickel core. All right. So if you were paying attention, I didn't say cobalt. And the reason why is the next one, by studying meteorites. Almost all meteorites are made of iron and nickel. All right. Iron and nickel. Mm-hmm. So we really don't see any cobalt in our solar system, very little. So we make an assumption really that, hey, we don't see it in the solar system, we don't see it in the crust, we doubt it's that element inside the Earth. We could be wrong. But the fact that almost every meteorite that hits Earth is iron and nickel, and since the meteorites, if you remember from earlier in the year, the meteorites formed from that big nebula that formed the rest of our solar system. So if we find a lot of iron and nickel in these leftover meteorites, then we are saying or assuming, hey, well, where's all that iron and nickel in Earth? So we believe we do have that iron and nickel. It just happens to be trapped in the core and it's not in the crust anymore. Okay? And the last thing, number 5, is Earth's gravity. Okay? So gravity is an invisible force that pulls one object to another. So Earth has actually a very strong gravity, stronger than it should be. Once again, what I mean by that is if we do that assumption earlier, if all the rocks on Earth were the same thing throughout, like the rocks we see on the surface were the same rocks in the core, then actually Earth would be a lot weaker with its gravitational pull. So there must be something inside Earth that gives Earth enough mass to have a very strong gravity. So when you actually add up 3, 4, and 5, it leads us to the conclusion that the core is made up of iron and nickel. So Earth's gravity, Earth has a very strong gravity for its size. So this could be explained by an iron and nickel core. All right? The rest of these notes kind of summarize or define the layers. So you should look at them on your own. So like defines the lithosphere, defines the crust. Let me just take a second with the crust because I didn't put a note there. So your continental crust is actually made of a type of rock called granite. And granite is a denser rock. Sorry, a less dense rock. So the continental crust is less dense and thicker than ocean crust. Okay? And it's made of a rock called granite. Don't worry about what this term felsic means. We'll come to that later when we learn more about rocks. So just know right now that the continent is made of rocks that are less dense and thicker. And the major rock that's there is granite, which a lot of you may have in your counters, kitchen counters. The ocean crust, which is the seafloor, is mainly a rock called basalt. And this rock is denser and thinner. Well, the crust is thinner than continental crust. Okay? And I always remembered that it was made of basalt because basalt has the word salt in it. And guess what seawater has in it? That's right, salt. But I don't really like using that analogy because basalt doesn't really have the mineral salt at all. It just happens to make the word. All right. The word literally means basalt or basement rock. So basalt, if you pronounce it like that, it makes it easier to understand, kind of makes up the basement of Earth, which is the seafloor. So if we got rid of all the water on the Earth, you can actually build cities and walk on the ocean floor. It'd be pretty cool. And it would be this featureless rock, black, smooth rock called basalt. All right. So read through the rest of this. There's some other complicated terms. One of them is called the Mohorovicic discontinuity. That's a really long word. No one likes to say it, so we just nickname it the Moho, and that's fun to say. So the Moho is just the boundary between the crust and the mantle, right? It's the only boundary that you need to know the name of, and it's in the chart we're going to study. All right? That's today's lesson, our first one on screencasting or Screencastify. I hope you enjoyed it. Always feel free to email me if you have any questions. If you don't understand seismic waves, like I said, we're going to spend a day or two studying them. And we're also going to spend the next couple of days with other charts studying Earth's interior. All right? Have a nice day.